Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 2, part of this playlist, which is Discrete Random Variables. And today's topic is the Hypergeometric Distribution. So, brief development and intuition. Assume we have a finite number of objects N with R of them success or the trait of interest. So, that means there's N minus R objects that are failures or not the trait of interest. So for example, flipping a head, we're interested in the number of heads. So head would be success, tail would be failure. Dead or alive, we could assign those depending upon we want to model the survival or the failure. Number of red balls in a box, number of blue balls. So if we're interested in the number of red balls that we sample, then red is success, blue or black would be failure. So that's the idea there. We're going to draw a sample size in objects without replacement. That means observations are not independent. And really, I think of hypergeometric as, think of a big box and all the objects are in there. There's two different traits, and we call them success or failure. And we're going to sample observations one at a time. And then we're going to calculate the probability that we observe, X successes. So if we let X be the number of successes in the sample size N, then the density of X is a hypergeometric distribution given by this expression here. It's the product of these two combinations, R choose X and N minus R choose N minus X, divided by the total number of ways we can grab N balls out of that box, N choose N. And I'm going to say box because that's literally how my mind visualizes it. We have a big box or a big bag with these two different traits in it. Now, X, you think the number of successes could be from 0 to whatever our sample size is, but it's not. If the population is small, we have just a few successes and just a few failures, and our sample is bigger than both of those, not combined, because then that's not possible. But then we have to put restrictions on the number of X, and that's what this maximum of 0 and whatever this number and the minimum of N and R, it really deals with if we have a small number of successes and or a small number of failures compared to our sample size. And I encourage you to go through some examples of just what I described, and you'll think, oh yeah, that makes sense. And it's kind of genius how they just set that up. Let's look at an example. Box 1 contains 7 red and 3 black balls. Box 2 contains 4 red and 5 black balls. A random ball is transferred from box 1 to box 2. 2 balls are drawn from box 2 without replacement. Find the probability that both balls are red, and we'll give a solution here. And after the solution, we'll do a R illustration, which is literally one line of code to simulate this 1,000,000 times. So let's let X equal the number of red balls, which could be 0, 1, or 2, right? We're drawing out 2 balls. T is the transferred ball color, could be red or black. Now, we want to find the probability that X equals 2. The number of red balls drawn is 2. That's equal to, we draw 2 red balls, given the transferred ball was red, plus the probability that we draw 2 red balls, given the transferred ball was black. We use conditional probability on these. Probability T equals R, given, or times probability X is 2, given the transferred ball was red, plus, and then this conditional probability. Now let's go through these. Now we just start plugging in numbers. So the probability that the transferred ball was red is 7 out of 10, right? There's 7 red balls out of 10. Then the probability that we observed 2 red balls, given the transferred ball was red. Now we think about it, we have our box. We know the transferred ball was red. So we have 5 red and 5 black balls, and we're taking out 2, and we want to find this the probability that X is 2. That's a hypergeometric distribution. So it's 5 choose 2, 5 choose 0, and then 10 choose 2, this number. Now let's move on to the next one. Plus, the probability that the transfer ball was black is 3 out of 10. Now the probability that we draw 2 red balls given the transferred ball was black. Now in our box, we have 4 red and 6 black. What's the probability that we observe 2 reds? So that's a hypergeometric distribution. So it's 4 choose 2, 6 choose 0, 10 choose 2. Now, when you do the math, you get these fractions. You multiply and add it, you get 44 divided by 225. And that's the exact probability. In one of the proofs here, we're going to use Vandermon's identity. And we'll need it to derive the mean and the variance. And I'm not going to derive this identity here. I have a video on my channel called Vandermon's identity. Actually, if you search Vandermon, 2 or 3 videos will come up. I highly recommend you watch all of them to really understand this formula. It's so powerful, and as a statistician, you may need it if you're going to derive certain theoretical results. So let's let x be a hypergeometric random variable with parameters n, r, and n. The mean of x is given by n times r over n. And that's it. And that's what you see in books. But I'm going to write it as n times r over n. And the reason I do that is because this reminds me of a binomial distribution, right? Our population has success or failure, and the mean of a binomial is n times p. P is the probability of success. And what is the probability of success before we start? In this box, we have capital N observations, and R of them are successes. So it's R divided by N. So this is P, the probability of a success. So it's N times P. So it's actually the same, essentially, as a binomial distribution. Okay. The proof, the expected value of x, is you take x times the density summed over all possible values. Now, here, like if x is 0, this term doesn't even contribute. So we might as well start at 1. And we're going to manipulate these a little bit. The second combinations will just carry over. R choose x, the r factorial on top, one of the r's will bring out, which leaves just r minus 1 factorial. This x cancels with one of the x's in x factorial, and it leaves this. Now here we're going to take out an n divided by capital N divided by little n, and it creates this. Now x is the index, so these two terms will come out of the sum. But before we get to there, we do a variable change, y equals x minus 1. Right? So the term, we subtract 1 up here. We could subtract 1 here, but I go ahead and put it into the arguments, 0 and minus 1. And then this right here is an application of Vandermon's identity, and it sums to 1. And we're left with r n over n. And for another proof of the mean of a hypergeometric distribution, see the video mean and variance of a hypergeometric distribution. I give another proof that's different from this one. Now let x be a hypergeometric random variable with parameters n, r, and n. The variance of x is given by this expression here. And this is what you see in books, this middle expression, the variance of x. But I'm going to kind of move these around a little bit. We have an n, then we have an r over n, and then an n minus r over n, and then this extra stuff. Now, the variance of a binomial random variable is np 1 minus p. And if we think about this, r over n is the probability of a success. N minus r over n is the probability of a failure, right? So that's npq, which is very similar to a binomial distribution. And this extra piece is what's called a finite population correction factor, right? We're sort of in the binomial setting, but we don't have an infinite number of observations. It's only a finite. So there's what we need, a correction factor when we calculate the variance. We're not going to prove this, but I prove it in this video, mean and variance of a hypergeometric distribution. So I highly recommend that you go watch that. Now here's the one line of code. It's actually, I have two, but you could stick a million in for in this formula. There'd be one line. And what we do is we sample. Remember, our box has 4 red balls and 5 black balls. And we're going to put in another red ball with probability 7/10 and a white ball with 3/10. And that's what this random binomial distribution does. Then we're going to sample 2 without replacement. We're going to add them, which tells us how many red balls we sampled. We're going to check to see if it's 2. We do this for every observation. Then we sum that whole vector, divide by n, and it gives us the probability of observing 2 red balls, which is 0.195506. That's the 1 million replications. That's our estimated probability. And in the example, our theoretical probability was 44 over 225, which is very similar to what the simulated value is. Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.